So to end up the measurement unit, we're going to talk a little bit about electromagnetic radiation, and then we're going to talk about using some relationships in electromagnetic radiation. So what is electromagnetic radiation? It's a fancy name for light. Now, when we say the word light, a lot of times we're thinking only of visible light, and electromagnetic radiation spans light that we can't see, so EM radiation is a little bit more precise of a term. But basically all of these have oscillating fields, and it has different properties, and these properties are where we're going to have some relationship. And we'll understand why we need to know this for chemistry a little bit later on, but for right now, we just want to understand the properties of these waves and electromagnetic radiation. So I have wavelength. Note that it's called wavelength, but it's going to be represented by a Greek variable. This is a lowercase lambda. So it looks like an upside down Y. And that is the distance between crests or between troughs. So this is going down. So this is like a trough, the lowest point, and then it goes up, and this is a crest. So if I go the distance from one crest to another crest, that's going to be my wavelength. Note that these are a little bit further apart. So this is a higher wavelength. This is a lower wavelength. These are a little closer together. The next one is frequency. How often do crests pass per second? Note that I can't see frequency on a picture because frequency is about motion. It's about time, and this is a static picture. But if I were watching this over time and standing in a particular place, and I were watching how frequently does a crest pass that particular point, and I timed that, that's going to be my frequency. So it is going to be in per second. So how many waves per second? So inverse second. It's a very unusual kind of unit. Also note that we don't call it frequency. We associate it with a Greek variable that looks like a V, but it's kind of a cursive V. It's the Greek letter nu. It's a lowercase nu. And then the last thing is it turns out that all of these electromagnetic radiation are moving at the same velocity of 2.998 times 10 to the 8 meters per second. So really we usually say 3.00 times 10 to the 8 meters per second. And that's the speed. Now it turns out that these two are going to be related. All these three are related, and we're going to use that information. Also note that wavelength is often reported using metric prefixes, so nanometers or micrometers, because rarely is it in a meter range. It's usually much bigger, many meters or very small. And frequency is often reported in 1 divided by second, or second to the negative 1 power. Really, these are the same thing, so we call these inverse seconds. But another name for that unit is a hertz, and this is often how we will see it. But note that hertz will not cancel out in calculations in the same way that seconds will. Also, I want you to understand the range of different kinds of electromagnetic radiation. So, and know the relative order. So we begin with gamma rays. They have very, very tiny wavelengths, 10 to the negative 12 meters. Then X-rays, a little bit bigger in wavelength. Then ultraviolet. And then we go to our visible range. Note that we start with blue or purple. It's actually, remember, if we're using our Roy G. Biv, this is my Roy, this is my red over here. Red, orange, yellow, green, blue, indigo, violet. So I have my violet is the shorter wavelength, and I go up to red, which is my longer wavelength. Note that the ultraviolet is a little shorter than the violet, and the infrared comes next, and that's a little bit longer than the red. So that helps you determine which side is which. So the violet is on the violet side, ultraviolet side, and the red is on the infrared side. And then we remember Roy G. Biv from our middle school years. So I move up to slightly higher infrared, and then comes microwaves. And then comes radio waves, which really exist as FM, shortwave, and AM. And technically, we have cellular signals in here now. This has all been kind of divided up into TV signals and cell pattern signals. So these are kind of up in here. We'll just call these all radio waves. We're not going to get into that. Okay, so I mentioned that frequency and wavelength are inversely proportional. The speed of light is the wavelength times the frequency. And so I can use this. This number is not going to change. The speed of light is a constant. I will give this number to you on a test, but you need to know to look for it, and you need to know that 3 times 10 to the 8 meters per second is the speed of light. That number's not changing. So now if I give you the wavelength, you have enough information to find the frequency. Or if I give you the frequency, you have enough information to find the wavelength. We also talked a little bit about these inverse relationships. If I were to put these on opposite sides of the equation, lambda is equal to speed of light divided by frequency, or frequency is equal to speed of light divided by lambda. So they have an inversely proportional relationship. And one thing we know that means is when they're inversely proportional, when one thing is big, the other thing is small. They're going to do the opposite things. If I increase the wavelength, I'm going to be decreasing the frequency. If I have a short wavelength, it's going to be associated with a high frequency. And that's very helpful just to have a sense of which way things are going to go. I'm also putting down here a simulation. You'll have to type it in or go to your notes to get the link. And this kind of lets you play with waves and change the frequency or change the wavelength and kind of get a sense of, in your mind, how these are related together. So I do want to remind you we are going to be dealing with a lot of the visible light, which is what we are going to be doing calculations with, is in the 400 to 700 nanometer range. And a nanometer, remember the nano prefix is 10 to the negative 9. So these are 10 to the 1 times divided by 10 to the 9th of a meter. Very, very tiny little units. And you're going to have to do a conversion. Remember back here, this is in meters per second. So I'm going to have to use my wavelength in meters and my frequency in hertz or inverse seconds. So I need to convert nanometers to meters. And people will forget to do this, and it's usually a big part of the problem. One of the easiest things is I just replace this nano with times 10 to the negative 9. And you can type this number into your calculator, 700 times 10 to the negative 9. Now, it's not in true scientific notation, because in scientific notation, I have to have the prefix number has to be a number between 0 and 10, and this is not. This is bigger than that. But if you type in 700 times 10 to the negative 9 in your calculator and hit equal, it will actually convert it to scientific notation for you and say, well, that's really 7 times 10 to the negative 7. But mathematically, this value works just fine. So I often use this as a quick conversion technique. I could also set up a dimensional analysis to convert it. That would work equally well. Okay, so converting a wavelength of 204 millimeters to frequency. Here's my starting equation. I rearrange it for the one I want to use, that frequency is equal to the speed of light divided by the wavelength. And if you really get struggling with these Greek letters, you write your formulas in terms of wavelength times frequency and just, use those letters. That's fine. You should recognize these because they're going to be in the textbook and in problems and things that I give you. But you can, for your own use, if it's easier to write these as words rather than funny letters, that's fine. And then this 3 times 10 to the 8th meters per second, this is the accepted value of speed of light. It will always be 3 times 10 to the 8th meters per second. And now my lambda, my wavelength, is up here, 204, but I have to convert those millimeters to meters. But I know that milli means times 10 to the negative 3, so I'm just going to put in 204 times 10 to the negative 3 meters. I complete this division. Note that, look at my units. I have meters per second on the top and meters on the bottom. So the meters will cancel and leave me with 1 over seconds. And I end up with 1.49 e to the 9. It's 1 over seconds as the units, but at this point I recognize, oh, I can call that a hertz. They are the same thing. Flipping it the other way, if I wanted to convert 650 megahertz to wavelength, I'm going to use the other form of the equation. Wavelength is equal to speed of light over frequency. I still put my same speed of light on the top. I put my frequency on the bottom, but remember this is megahertz, so I'm replacing the mega with its prefix value of 10 to the 6. Note that I have meters over second divided by 1 over second, so the seconds cancel and I'll be left with meters. And this is 4.615 times 10 to the negative 1 meter. I can convert that to standard notation of 0.462 meters. Note that in these cases I had 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs, so I can keep 3 sig figs in my final answers. In class, we're going to practice this. What is the frequency of green light? which is has a wavelength value of 540 nanometers. And what wavelength is the KSLU radio frequency, which operates at 90.9 megahertz.